Good day. In this lecture, we will discuss the chemistry of the soil, focusing on its composition and colloidal properties. By the end of this lecture, you should be able to discuss different types of soil, their colloids, and their properties. The geosphere refers to the solid part of the earth, including rocks, minerals, and landforms. The soil is derived from this system. These slideshows show the internal structure of the earth, and the outer layers, especially the crust, are the primary sources of soil materials. First, we have the crust, which is the outermost layer and is the least dense of all the layers. The crust is made up of solid rock from mostly silicon and oxygen. We have the second layer, which is the mantle, and it is also considered as the thickest layer. The density of the mantle increases with depth due to increasing pressure. The mantle in this case also contains iron and magnesium. For the core, it is made up of two parts, the outer core and the inner core, and it is the heaviest material among the Earth's layers. The core is mostly made up of iron and nickel, and the outer core is a slow-flowing liquid, while the inner core is a spinning solid. The Earth's surface is mainly composed of oxygen, silicon, aluminum, iron, and other elements. These form the basis of soil metals. In terms of the types of minerals, the lithosphere contains silicate minerals, carbonate minerals, oxide minerals, and sulfide minerals. These determine soil composition. For silicate minerals, those are compounds of metals with silicon and oxygen. For carbonate minerals, those are metals combined with carbon and oxygen. For oxide minerals, those are metals combined with oxygen only. And for sulfide minerals, those are metals combined with sulfur only. Examples of these minerals include hematite for iron, chalcopyrite for copper, and calcite for calcium carbonate. These minerals influences soil chemistry. Soil is the upper layer of the earth where plants grow. It is a mixture of organic matter, minerals, and weathered rock. Soils are developed through the process of weathering. Weathering is the alteration and breakdown of rock minerals and rock masses when they are exposed to the sun, wind, rain, or organisms. Weathering can be classified into three types. The first one is physical weathering, that is the mechanical disruption of rocks. Chemical weathering caused by bases, mild acid, as well as water and temperature. We also have biological weathering due to vegetation, animals, or microorganisms. Erosion is the removal or transport of weathered or broken rock materials downslope and away from the original site of the weathering. Erosion may be aided by gravity, wind, or water. Soil develops into layers called horizon, including a leaching zone and an accumulation zone. These layers influence nutrient distribution. Under zone leaching, we have O or humus or organic layer, A for topsoil, and E for eluviated horizon. For the zone of accumulation, we have the subsoil and the parent material. And then lastly, we have the bedrock. Soil colloids are the smallest and most chemically active particles in the soil. They determine many physical and chemical properties. There are four main types: crystalline silicate clays, non-crystalline clays, iron and aluminum oxide, and organic colloids or humus. For crystalline silicate clays, we have phyllosilicates, which are tetrahedral and octahedral crystal sheets. For non-crystalline silicate clays, we have andisols, which are dominantly amorphous clays such as allophane and imogolite. For iron and aluminum oxides, we have oxysols, dominantly gibbsite or aluminum oxide, or goethite, which is ferric oxide. We also have organic and humus colloids such as histosols, and these are non-crystalline colloids dominated by long carbon chain molecules. Phyllosilicates are sheet silicates composed of interconnected tetrahedral units. They form the layer structure in the soil. This structure consists of silicon-oxygen tetrahedra, and they are arranged in sheets. This structure influences water retention and ion exchange. Many phyllosilicates contain hydroxyl group, which contribute to chemical reactivity and charge properties. Examples of phyllosilicates are talc, the microgroup minerals such as muscovite and biotite, and your chlorite. These differ in composition, structure, and occurrence. Under phyllosilicates, we have talc, also called soapstone. It has the formula Mg3Si4O10OH2. In terms of its occurrence, talc can be found in low-grade metamorphic rocks that originated as ultrabasic to basic igneous rocks. These are rocks composed almost entirely of talc, have greasy feeling, and referred to as soapstone. In terms of the rock cycle, the igneous rock can be converted into magma via melting, and the magma can be converted into igneous rock via cooling. Igneous rock can actually be converted directly to metamorphic rock using heat and pressure, and metamorphic rock can be converted into sediments by weathering and erosion. The same thing is true for igneous rocks. The sediments become compacted and undergoes the process of cementation to form sedimentary rock, which under heat and pressure can also be converted to metamorphic rock. We also have the mica group under phyllosilicates. Under this, we have muscovite and biotite. And for muscovite, it is common constituent of aluminum-rich medium-grade metamorphic rocks. The muscovite can also be found in siliceous, aluminum-rich, plutonic igneous rocks such as muscovite granites, but has not been found as a constituent of volcanic rocks. Muscovite has white to sometimes light brownish color. We also have your biotite, which can be found in hydrous ultrabasic rock like kimberlite, and they are common in trachytic volcanic rocks and granitic plutonic rocks and a wide variety of metamorphic rocks. Biotite can sometimes be brown to black in color. The next type is chlorite under phyllosilicate, which has a complicated chemical formula. Chlorite is common mineral in low-grade metamorphic rocks where it occurs in association with minerals like actinolite, epidote, and biotite. In hand specimen, it is characterized by its green color, maybe green to pale yellow. The next type is andisols. These are non-silicate crystalline clays, for example, allophane and imogolite. The volcanic ash is chemically or mineralogically distinct from most other soil parent materials. Andisols is composed largely of vitric or glassy materials containing varying amounts of aluminum and silicon. It lacks a well-defined structure and is quite soluble. Allophane and immogolite are common early-stage residual weathering products of volcanic glass and both have poorly ordered structure. Allophane form inside glass fragments where the silicon concentration and the pH are high and has a characteristic spherule shape. For immogolite, it tends to form on the exterior of the glass fragments under conditions of lower pH and lower silicon concentration and has a characteristic thread-like morphology. We also have sesquioxides or oxysols, and these are iron and aluminum oxides. They are dominantly gibbsite in the form of aluminum oxides and goethite in the form of iron oxides. They are found in many soils, especially important in highly weathered soils of warm, humid regions. And some, such as gibbsite and goethite, form crystalline sheets, and the others form amorphous coating on soil particles. The surface plane of covalently bonded hydroxyl group gives these colloids the capacity to strongly absorb certain ions. Under histosols, we have humus, which can also be called organic soil colloids, non-crystalline colloids dominated by a long carbon chain molecule. Histosols and humus are important in nearly oil soils. They are not mineral or crystalline in structure. They are consisting of long convoluted chains and rings of carbon bonded to hydrogen, oxygen, and nitrogen. Humus in this case have very high capacity to absorb water and have high amounts of both positive and negative charges, but the net charge is always negative. To summarize, soil composition is controlled by minerals, weathering processes, and colloids. Colloids are the most important component in determining soil behavior. That concludes the lecture on soil chemistry. Focus on how colloids influence soil properties and nutrient interactions.